the makeup practical is going to be here tomorrow. So those of you who weren't able to make it last week, here tomorrow it'll happen instead of a lecture. And then the following, and then at the end of the week, on a Friday, the next track will be upstairs in the archaeology department in the teaching studio, and that's where it will regularly be. So I'm sorry about whatever happened last week. Somewhere between England, which I think is where Vincent is, and here, there was some kind of miscommunication. I'm sorry about that. We were talking a little bit about stratigraphy, and I think what I was saying is that you always have stratigraphy. When you're excavating a site, you obviously have some kind of stratigraphy. It may be very simple, maybe very complicated, maybe very disturbed, maybe very hard to read, but it's always going to be there. In other words, the stratigraphic context in which you're finding things is your first clue as to how old things are, and also it's going to give you a lot of other information about the environment in that place at that time and so on. But the problem with stratigraphy is that, first of all, it can be incredibly complicated, something like this, so you may have a lot of trouble figuring it out. You'll obviously have to do that. But if you want to make comparisons between one place and another, it's not going to allow you to do that. The stratigraphic information about relative age only works within a single stratigraphic context. So if you want to make comparisons between one cave and another cave, because caves are very good examples of bounded stratigraphies. There is a stratigraphy in that cave. You might have a cave 20 meters away, it might have a completely different stratigraphy. So if your hypothesis or the kind of narrative that you're trying to develop means you have to understand between caves or between stratigraphies, it's not going to help. Sometimes you're very lucky, say in Alderby Gorge, for instance, which is several kilometers long, and there are lots of very, very important sites. There is a common stratigraphy through the gorge. And so you might be digging 15 kilometers from another person, but it may well be possible for you to find a datum horizon that goes all the way through the gorge, let's say a volcanic eruption, which you can identify, and then if you know where your artifacts are in relation to that datum horizon compared to another, you can do something. But obviously what you would really like is to move from the relative chronology of a stratigraphy to the absolute chronology of a scientific dating technique like radiocarbon dating, although that won't work at Alderby because Alderby is too old. But there are equivalent isotopic methods, potassium argon dating, for instance. So that's stratigraphy, very valuable, and you obviously you're helped, and but there you see this horizon is bounded. Even within a narrow space, you might have a hearth or a layer of grass bedding that people have, and it's very localized. So the problem with relative stratigraphies is the localization of those strata and the difficulty of applying them on a large scale. And your issue, and Vincent's got some good issues later, the issue may require you to have knowledge over the whole of southern Africa, for instance. And stratigraphy is not going to help you there. You're going to need something that gives you absolute dates that are comparable over long distances. 45,000 years ago is the same 45,000 years ago in France as it is here in Cape Town, because it's absolute. Okay, so stratigraphy was one of the earliest aids for archaeologists to know relative age. It was extremely valuable. The other way of determining relative age was typology. And so Vincent starts it out by talking about faunal succession. What he's referring to here is that species live in recognizable order through time because as they evolve, their form changes in a kind of logical, predictable order. It's not jerky and complicated, but you can get to know it. And you might even be fortunate enough to have those changes happen over quite a large area. He gives an example here of when people were trying to understand the age of fossil sites in southern Africa, they looked at the animal bones that were associated with the fossils, and they said, well, if I were in East Africa, this animal would, would fit here in the sequence. I've got that same species of elephant here, or that same species of rhino, or that same species of bear. Sorry, bad example. No bears in Africa, except the one at the fossil park. But you might have 5 animals with your fossil here in southern Africa, and you're trying to figure out how old it is. And those 5 animals you might take to East Africa, and you might, in each case, get an estimate that it's early Pleistocene rather than middle Pleistocene, or it's late Pliocene rather than early Pleistocene, or whatever. And then you might have some confidence, but it's still not perfect, because, as he says here, what if a species survives in one area, say in southern Africa, and it's gone extinct, or evolved into another species in East Africa? So this is not perfect. So faunal succession is a kind of typology being worked through the evolution of different genera and species of a particular animal that allows you to put things in relative order as stratigraphy did. And of course you're reading it alongside stratigraphy. So both stratigraphy and typological change are working together, and they work well at a local area, at a local scale. But they are less useful when you want to work at a larger scale, and when the assumptions at one place don't necessarily apply at the other place. Typology alone. So until let's say 1950, when radiocarbon dating came along. Until that moment, most of our understanding of the relative ages of things was gained through a combination of stratigraphy and typology, and it was all we could do. That's why radiocarbon dating was such a breakthrough. And so you had people constructing typologies of everything they were finding. If you like, typologies of animals represent the allocation of animal bones to particular genera and species. Typologies of artifacts were constructions of the sequence in which a particular kind of artifact, an axe, so you've got these axes evolve through time because the form, the shape, the size, some detail of its construction is changing gradually in an organized fashion through time. And so when you get something new, you can fit it into that sequence. So this is all about sequence. Stratigraphy and typology are all about sequence, but the sequence has no calibration. It does not tell you an absolute age, and obviously it can't tell you how fast things are changing. Right? Those are the disadvantages of those relative methods. So beginning, and I'll go through this quite quickly, I can see that this would be very interesting to Vincent, because he's looking here at the application of science and scientific knowledge into archaeology to take us from the age of relative chronology to the age of absolute chronology. And Marie Curie discovering radioactivity. But a lot of these methods that he's going to talk about in great detail are based on radioactive decay of particular isotopes like C14 or potassium, or radioactive isotope of potassium or uranium and so on. Once isotopic decay methods got into archaeology, they were expanded and they've become fundamental to what we do now, because the radiocarbon date or the potassium argon date that you get in East Africa and South Africa will be absolute and directly comparable, regardless of the certificate. I've no idea what the chap on the right is doing. No, but you probably do, because you've heard Vincent talk about it. Okay, good. And part of the early work on isotopes and dating methods was directed towards understanding the age of the Earth, because that obviously, once we had good ideas about the age of the Earth, that gave us an idea of the time span within which human evolution and all of evolution could play itself out. And that's crucial because, of course, to do some of the things, to make some of the changes that Darwin was talking about, you need time is the crucial element. Given a lot of time, you can have a lot of change, even if it's slow. And here's the key moment. In 1949, Willard Libby, based on the discovery of radioactive isotope of carbon, began to realize it could be applied to archaeology. And so what he did, obviously, was he got some organic materials of known age. In order to test it, he had to say, I know this is 5,000, I know this is 2,000, I know this is 1,000. Now let me apply the radioactive decay of carbon-14 to those objects. Let me date them and see if it works. And of course it did. It was very crude in those days. As I understand it, they were kind of painting the sample on the outside of a Geiger counter and counting the ticks of the counter as it went up. Very, very crude and very different from the way it's done today, obviously. But it worked. So he had samples from some Egyptian tombs where the date of the wooden objects or whatever were known, and he was dating them, and as you can see, and he got the Nobel Prize for promoting the application of that technology into archaeology. And it's, as Vincent says here, it's the single most important dating method today. The reason why it isn't the only dating method is because it has a limited time span. What it's measuring is the decay of the radioactive isotope of carbon, C14, as a ratio of the non-radioactive isotopes of carbon, which don't decay, C13 and C12. So it's that ratio, because we know, well, I'll talk about this later, because we know what the ratio of C14, C13 and C12 is in us, because we have hair, nails, animal bones, charcoal, shells, anything that's alive, we'll say this at this stage, but we'll have to modify it later, has that ratio of C14, C13, C12. But obviously, since the C14 is decaying at a known rate, every C14 atom decays randomly, but after a given amount of time, there is half as much left as I started with. And we know what the ratio is today. So we know that after 5,730 years, or whatever, there will be half as much. And after another 5,730 years, there'll be a quarter as much, right? And so on. It halves every 5,700 years. So the problem is that eventually there's so little of it left that it's very hard, even with our much better measuring techniques, it's much harder to measure and to distinguish from surrounding, for your machinery to distinguish the radioactivity that's coming from your sample from the ambient radioactivity in the air. That's why in Pretoria, when they built the lab in Pretoria, they sunk it down a shaft, I don't know how many meters deep, but kind of 20 or 30 meters underground, to try and shield it from the radioactive activity that would be in the atmosphere. That's why painting it on the outside of a Geiger counter was a very risky and crude kind of method. So, so by the time the original amount of C14 in a bit of shell that you want to date, or a bit of bone that you want to date, by the time it's halved 6 or 7 times, there's so little of it left you can barely measure it. So radiocarbon dating just ceases to work on organic material above a certain age. But fortunately, as you can see there, uranium series and others, there are other techniques that we can use going further back in time. But for a long time, we were really stuck with the boundary of radiocarbon dating. Yeah.
Is there a reason that obsidian hydration dating is a hard line on either side, whereas the others seem to be? Same with the C bond.
Oh, over there.
Yeah.
I think that's kind of the present, isn't it? No, that's the back. I don't know. You'll have to ask. I think most of these techniques can be, kind of tinkered with to make them, get a bit further back in time, or in some cases further forward in time. The problem with uranium type dating is it's not very. It's the opposite problem to radiocarbon dating. It's not halved too much. It's not halved enough because it's got a very long half-life. So the problem with uranium is, making it work on relatively recent samples. The problem with radiocarbon is making it work on older samples. In the case of obsidian hydration dating, I don't know why we have that. I'm not sure. It may even, see, it's got it at both ends, hasn't it? Yeah. I don't know. Sorry. So, so you can see then why radiocarbon dating is so incredibly valuable, right? It allows these long distance comparisons, and it allows you to tackle problems where you need to be able to apply it over large areas. And of course, it extends chronologies way back beyond historic records. Exposing hoaxes, I think what he's got in mind there is that there were some very well-known hoaxes. Well, one in particular, actually, the Piltdown hoax, where British paleoanthropologists were very conscious that everything was happening all over the world, but not in England. All these early hominids were being found in Southeast Asia or in Africa or wherever, and it had been their hope that British paleontology would be important. It's not just the Brits, but they had hoped that their fossils were as significant in human evolution as the ones that were being found by then in Southeast Asia and in Africa. And so somebody salted this river gravel in southern England, and this was in about 1911, 1915, and it took the discovery of radiocarbon dating and the application of radiocarbon dating to this issue for that to be shown up. One of the cranium of this supposed early hominid was in fact an orang skull and teeth, which had been carefully broken so that the pieces that would obviously have identified it as an orang were not there, and the wear on the teeth, which would have obviously distinguished it from the wear on the teeth of a hominid, had been filed and stained. But eventually, when radiocarbon dating was available, and some other techniques actually, they found that the orang cranium was modern. It had a radiocarbon age of virtually nil, and the mandible was a Neolithic 5,000-year-old mandible. These have been put in pan. Okay. And various other. It's been enormous, and I think Vincent is absolutely right to say that it is the single most, combined with stratigraphy for local relative understanding, radiocarbon for absolute broader scale understanding. Those are the critical dating methods, unless you do obviously. So he's showing here that our understanding of the demise of Neanderthal people in Europe. Remember the Neanderthals were a separate species who were found almost only in Europe, although at one stage it was thought that they might have been in North Africa, but it was not generally claimed to be the case now, and on the fringes of Asia. How, where, and when did they become extinct? And by dating Neanderthal remains all over Europe, something of the shrinking of their distribution and their survival, apparently in the peninsulas of Spain, Italy, and Greece, some kind of notion of how it was they disappeared, and whether they disappeared at the time when modern Europeans from Africa were first penetrating Europe, or whether there was coexistence for a while. All of that stuff can be done with radiocarbon dating. And then the spread of domestication in southern Africa. We know, I think it's fair to say, that Khoisan, San effectively, San hunter-gatherer people were all over southern Africa, up actually as far as the Zambezi and the Kunene, and that they were the only people in southern Africa until fairly recently. Subsequently, farming communities penetrated from the north, and they became the ancestors of modern Zulu and Xhosa-speaking people. And then, of course, European penetration from the south. But the interesting issue is the gradual dispersal of domestic animals in southern Africa, and that's been pretty well sorted out by radiocarbon dating. Then the third example he gives is the Turin shroud, which is a shroud with this image, which was thought to be a shroud that was laying over Christ at one point, and took from the body fluids, took on the image of him. And there's a lot of argument about whether it was or whether it wasn't. What they did was they submitted samples of that shroud to 3 different laboratories. There are radiocarbon dating laboratories all over the world, of course, lots of them. Some of them are commercial, some of them are more academic. And these were the dates that they got. So they achieved some resolution by doing a blind test with 3 different labs. It's medieval, it's not 2,000 years old. You can, radiocarbon dating, you can, or C14, you can apply to anything organic, anything that was alive at one point. It's got an age, as I say. It's hard to do things more recent than about 300 years old because the Industrial Revolution started taking carbon, coal basically, and oil eventually, that is very ancient, and releasing it into the atmosphere. And so our C14 composition, our carbon isotope composition, C14, C13, C12, not the same as before the Industrial Revolution. And of course, the explosion of atomic bombs accentuated that. So we have got a problem in the last 300 years. We'll talk about that just now. And we can't get back beyond about, well, that's a bit of a fuzzy boundary actually. Many people believe that it's not really very reliable beyond even about 35,000 years. but there are ways of extending that that span by not measuring the relative frequencies of the isotopes, but by actually counting the number of C14 atoms, which is obviously very small, and using special counting techniques to do that. Those are the relative frequencies of, and that's the concept of the half-life. So what happens is it halves every 5, 7, 3, 5, 5, 6, 8, plus or minus 30 years. And of course it's very important to know what you're dating. Not what you're dating in the sense of what your sample is, but what is the event in the past that you're dating. If you date a piece of charcoal, you're not dating the time when the fireplace was lit. And you might, that's actually maybe what you really want to know, because you want to know when the floor and the site of which the fireplace is part was being occupied. That may be what you really want to know. What you're dating is the death of the tree that is used as the wood in the fire. And there may be a difference in time between that. So it's very important that you know what your target date is, I think the phrase you used, and what you're actually dating, and to make sure that those are the same, or you understand if they're not the same. Death, that's what you're dating. Now, you have to calibrate the dates, because one of the basic assumptions, which I've already said is wrong, is that standard ratio between C14, C13 and C12 is constant, and that the decay of the carbon-14 isotope is constant. Those are crucial, because obviously if you don't have those pieces of information, you can't work out the amount of time that the C14 has been decaying, has been halving, which is what the method does. And unfortunately, we know not only have there been problems in the last 300 years when the amount of radioactive carbon in the atmosphere has been increased by burning fossil fuels and exploding atomic weaponry, but it actually has always been varying. People who don't like radiocarbon, I mean, you know, there are a lot of people in the world who don't like radiocarbon dating because they don't like the apparent support it gives to very long ages for events. For various reasons, they don't like that. So they will point to this. They will say, yes, but in fact, the assumption that those isotopes have always been there in the same ratios is not right, and it isn't right. But it can be calibrated. In other words, we can go back in time with pieces of organic material of known age and calibrate the radiocarbon dating curve. And this is often done by using tree rings. So that's a bristlecone pine down there from Arizona, I think. And these are very long. These trees live for several thousand years, and they lie on the ground once they've died for more thousands of years. So what people have been able to do is to measure, is to core the trees and look at the tree rings, the annual growth layers of the tree, and measure the relative thickness of them and produce a kind of a curve going through the living tree, and then to take a dead tree and bring it alongside the core from the living tree, match them up and get even further back in time. So and they do that now with other kinds of trees in other parts of the world. But it's very hard to do that with short-lived organisms. You need a good long sequence of fluctuating tree rings to be able to recognize a unique sequence and then match that up with an older tree, which is, you see what they're doing here. So these rings, that pattern in there, being matched up with an older tree there, that gets you further back, and then an even older tree gets you further back. But you can see we don't have a calibration curve going back tens of thousands of years. We might have a calibration curve, I don't know what the maximum is, but say 15,000. It's quite good for the Holocene. It's quite good for calibrating Holocene dates, 5,000, 10,000, 12,000 years. But it doesn't enable us to deal with this problem going much further back in time. But you can see this is all science. There's a core that somebody has taken out of the tree, out of a tree. And it has limited application, tree ring dating in and of itself. As a calibration, it's quite useful, but as a method of dating, it's incredibly accurate because each tree ring is 1 year. So theoretically, you can identify in your piece of wood, let's say a beam out of this house here, you can identify a particular year. Great. That's more accurate than radiocarbon dating. Radiocarbon dating always carries with it this plus or minus, whereas tree ring analysis is very, very precise, but it doesn't get you back very far, and it has very severe requirements in terms of wood in a behavioural context that you want today. So all of these methods that Vincent's going through here, they have variable levels of precision and variable applications. Some are only applicable to very particular circumstances, some are much more general. So archaeologists use whatever method they can lay their hands on in the circumstance that they're investigating. And they'll use more than one. If they've got more than one technique of arriving at a date or whatever it is that they think, they'll do that. And eventually, of course, other methods of dating that also have, theoretically at least, annual precision. Eventually, people started coring the sediments on the ocean bed. Archaeological deposits with interesting material in them are very patchy across the globe. And so if you wanted a paleoclimatic record, if you wanted a record of climate change, you could only get a bit of it in any one place. Unless you go to the bottom of the ocean and you drill in the bottom of the ocean. 1950s this started, and people started using very sophisticated coring techniques to drill thousands of meters down under thousands of meters of water. And of course, at the bottom of the ocean, sediments are depositing continuously. They're not as disturbed as sediments on land. And they include within them organic materials. So living in the ocean are these little organisms with shells. They're very, very tiny. But the shells are also dropping to the bottom of the ocean. So the sediments on the ocean bed are organic, partly organic, and continuous. And so people drill those, and you get a Pleistocene record going back, 1.8 million years, even longer. And it's theoretically annual, but nobody's living at the bottom of the ocean, so its application to particular human behavioral issues is not the point. The point is it gives us a continuous paleoclimatic record, and it was the beginning of our understanding of long-term climate change, leading to an understanding of some of the changes that are happening in the last 100 years or so, and the issue of human involvement in climate change. But even better than the bottom of the core were the layers in the ice. And people started drilling through the ice, where you also get a theoretically annual record of climate change. Volcanic eruptions all over the world are spewing out ash and those that ash is settling in Greenland. They were drilling in Greenland and in the Antarctic. And so here you have fantastic records going back millions of years, relatively continuous, not constantly being disrupted and altered as sediments are on land. And the ice cores now are fundamental in our understanding of climate change. And that's why we know that the ice cores are why we know that the recent changes in the Earth's climate are humanly introduced, or at least correlate chronologically with the events of the last 200 or 300 years in human behavior. Because, why? Because we can see the glacial, interglacial cycle going on and on and on through these cores, and we know what the limits of this variability are. We know that if you go back 2 million years, the carbon dioxide parts per million changes with the ice age on a kind of 100,000 year cycle. But we know that the change doesn't go that way beyond there and doesn't go that way beyond there for 2 million years. It's happening within those bounds. So for instance, the parts per million goes between 150 and 250 thereabouts. We're now at 325. So there is absolutely no doubt that what we're seeing is something that's happened over the last few hundred years, and it is unprecedented in the last 3 million years. That doesn't mean that it's human, of course. You might have another hypothesis, but it's strong support for the idea that it's behavioural change that's brought about.
When you speak about those glacial, the maximum amount of carbon dioxide, is that including mass extinctions that have happened in the past, like volcanic mass extinctions? Because there's been 5, right? So have there ever been, specifically carbon dioxide, massive spikes like the one we're experiencing now?
No.
So this is
As I understand it, and I'm not a paleoclimatologist obviously, but as I understand it, these are the measured boundaries of change, and it's not just in parts per million carbon dioxide. It's also you also find those same boundaries in other measurements, because you can measure all kinds of things in the deep sea cores and in the ice cores. So whatever, and it's remarkable actually. If you maybe you've looked at them already, but if you look at the ratio between oxygen 16, oxygen 80, it's the same curve. So you're measuring chemically 3 or 4 different things going back a long way, and you're finding the same thing. That there's a 100,000 year cycle, and then actually before you get to 2 million years, it shifts into about a 45,000 year cycle. But it's there in whatever you measure, and that gives you confidence that it is it's a globally patterned phenomenon that you're measuring. And then you carry on measuring it up through the last few hundred years, and it's unprecedented. Is that,
Yeah.
Right. So that's yeah. In the top end of those cores, whether they're ocean cores or ice cores, you've got organic material, and you can use radiocarbon dating. Further back in time, you can use other methods. Luminescence dating is extremely important. One of the things that most of us down here are busy with is the emergence of modern people 50 to 150,000 years ago, and the subsequent spread of modern people out of Africa and colonizing the whole world. That's why we're all related to people who lived here 100,000 years ago, wherever we were born. because that explosion of modern people out of Africa effectively replaced any archaic peoples who were there with modern people with a certain amount of genetic exchange. And luminescence dating is very important. Why? Because it'll get you, if modern people emerged here in southern Africa 60, 70, 120,000 years ago, you can't do that with radiocarbon dating. It's too far back. And that was our problem. I was hinting at that just now. We found lots of things seem to be happening at 45,000 years ago, you know, and that was not because everything was happening 45,000 years ago, but that was the limit of radiocarbon dating. And if something that you were trying to date was 72,000 years old, it told you it was 45 because that's the best it could do. And so we kept, you know, it was becoming quite, Neanderthals were going extinct, you know, this was happening, that was, you know. So you needed another method to get back beyond 40,000. Luminescence dating was really, and that's one of the earliest applications was because little sand grains contain within them clocks of radioactive material, where it might be potassium, or it might be carbon, or it might be something else. But those things were decaying inside the crystal structure and were being trapped in the crystal structure. So that little quartz grain was a clock. It was just accumulating age. But when it gets released and blows in the sunlight, the sun blanks it, you know, releases all that stored energy and sets the clock to naught again. But then if it gets buried in your archaeological cave and is taken out of the sun's impact, the clock starts ticking. And so this was extremely important in our recognizing that modern people did evolve in southern Africa, because John Fogel, actually, who was the radiocarbon dating man in Victoria, was a wonderful guy and very smart, and he ran the radiocarbon dating lab in Victoria, and he realized that his radiocarbon dating was reaching a boundary and just couldn't tackle the origins of modern people. So he invited a whole bunch of people who he knew were beginning to experiment with this, and they started working on our site. And what they discovered is, of course, if you in the sediments that are built up with a lot of quartz grains, you can drill into the sediments. You've got to when you're taking the samples of these quartz grains, you've got to keep them out of sunlight, obviously, otherwise they'll immediately get bleached, you know. So, you know, you at night when you've got clothing, or you take a core, and so the grains that you're going to date are housed in the core, and they're only opened under special circumstances in the lab, and then the stored radioactivity age is allowed to be released under controlled circumstances, and you can measure the amount of light, luminescence dating, and you can measure that in various ways, and then, well, of course, you'll realize the amount of light depends on what is actually in the quartz grain, but you can measure that. See, radiocarbon dating and this kind of matrix, it's all based on science and on controlling all the variables until the only variable that you don't know is time. If you know how much radiocarbon dating, how much of the radiocarbon isotope there should be, and if you know how fast it decays, and if you can measure it, the only variable left is time, the amount of time since it's been harvested. And it's the same with this method. You know, you have to. It's about controlling for the variables until you can assume that those grains are such and such an age. And luminescence dating will get you back hundreds of thousands of years. So it's just the kind of thing people were looking for to get further ahead. Thermoluminescence is very similar to luminescence. It's just that you as well as the stored energy being released by the sun can be released by heat. So if those quartz grains are sitting next to a fireplace in the past, the fireplace will allow a stored age to be dissolved. But then when it is taken away from that source of heat, then time in the form of stored energy begins to go up. And you can date ceramics. In other words, thermoluminescence will allow you to come very close to the pressure. OSL, very similar. It's all about taking what we know about radioactivity and isotopic variability and putting it to use to develop a situation where the only piece of the equation that you don't know is time. Then you can uranium to. Let me just tell you this one, it's one of my favorites. So, turns out that the north and south poles eventually change places. It's quite a strange notion. And it's not regular, so it's not every 500,000 years or whatever, but they do. There's a geomagnetic reversal of the poles of the Earth, and we can measure that. And that's not an absolute dating method, but if we combine that with let's say, potassium argon dating, then we can build up a framework that we can apply to other sites. So often what's happening is several of these techniques are being combined. Olduvai Gorge, a good example. You can do all kinds of things at Olduvai. You can do stratigraphy, you can do faunal change, but at the top you can do radiocarbon dating, lower down you can do potassium argon dating, you can find geomagnetic reversal. So you do all of that. That's the principle behind this variety of dating methods, is they can act as a check on one another. And sometimes they need one another in fact to work, to be calibrated. So, I mean, that's really valuable. The other thing about the Earth's polarity is that the orientation of the north-south and the strength is also changing. So in the last few hundred or few thousand years, you can sometimes get an estimate of the age. We were trying this here. You can get it because you can build a time scale which uses the change in the angle between true north and magnetic north. That's varying, and in some cases it can help you date fairly recent things, ceramics, fire. Those floors at Gunung that I was telling you about. We tried it there. Theoretically, when the burning roof fell down and baked the floor, it would have baked in the magnetic characteristics of the Earth at that place, at that time. And if you can build a chronology of how that was changing, then you could take an unknown, fit it into the sequence. Didn't work in our case, but I'm not quite sure why. That seems like a good place to stop. Okay, so remember tomorrow, as I understand it, Zach, it's the people who didn't make the practice last week will come tomorrow here for the makeup track, and at the end of the week, the practice will resume for everybody